Section 2.1 is our introduction to inductive reasoning. Inductive reasoning is finding of a pattern and writing of a conjecture. Now, a conjecture is a statement we're going to see often in this chapter, and it's an unproven statement based on observations. The fact it's unproven means it could be either true or false. So the statement itself, either way, is a conjecture. Now, whether it's true or false, we have to go on later to determine, but it's just a statement unproven. And we say observations, and this is really a key thing for an inductive reasoning. We look for patterns, we look at examples, we look at observations, and we can make statements. Now, whether, again, it's true or false, that remains to be seen, but it's still observing something and then coming to a statement. This is something we can use to help us solve problems, but when we get down to actually verifying or justifying our answers, we have to kind of get away from inductive reasoning because specific observations won't always verify a correct answer. And we'll see that actually in section 2.3, which is deductive reasoning. But back to a conjecture. We said it could be either true or false. Now, if it's found false, we need to find a counterexample to it. And a counterexample is just a way to prove that it doesn't work. Now, for a counterexample, we need just one. Now, maybe there's more. Maybe there's an infinite amount of counterexamples we could find, but as long as we find just one, it verifies that it doesn't work. It's kind of an all or none situation. It works in every possible case, or if it doesn't work in one, it doesn't work at all. So we're going to make and test our own conjecture, and we're going to look at the sum of any three consecutive integers. And we talk about consecutive integers. Those are any whole number could be positive, could be negative, it could be 0. So 3 consecutive. Well, we'll start with the easiest one. 1 plus 2 plus 3. We're looking at its sum, and that sum is 6. Okay, maybe the next set. How about 3 plus 4 plus 5? That gives us 12. So we're looking for a pattern, so see if something develops. So far I have 6 and 12 as my answer. And that actually gives me a lot of options it could be. It could be an even number anytime we add the 3. It could be a multiple of 6. It's all positive. So that's not specific enough yet. We need to keep doing more examples. So let's say we do 4 plus 5 plus 6. That gives us 15. 7 plus 8 plus 9 is 24. 10 plus 11 plus 12 is 33. So we've gotten a few samples here, and we can maybe get an observation from that. They're still all positive, but maybe if we did negative 1 plus 0 plus 1 is 0, that kind of gets rid of that thought. They're all multiples of 3. That's something that exists. So let's take a look at that a little bit further. They're all multiples of 3. This is 3 times 2, 3 times 4, 3 times 5, 3 times 8, 3 times 11, and although that's 0, that's 3 times 0. So we could actually state the conjecture here that it is the sum of any 3 consecutive integers is a multiple of 3. That would be true, but we can actually go a step further. If you notice the middle value in all of these, it matches to the number multiplied by 3. 2, 4, 5, 8, 11, 0. Same thing over here. So our actual conjecture will be the sum of any 3 consecutive integers is 3 times the middle value. So that's our statement. If we could find a counterexample, that would prove it false, but I have a pretty good feeling this one is going to hold up. We could even look at maybe some negatives. This could be negative 12, which is 3 times negative 4. We could look at big numbers. 100 plus 101 plus 102 is 303. Just 3 times 101, so that one's going to work. We could look at fractions, but we've already said they're integers, so they have to be whole numbers. So we're pretty safe to say that is going to be our conjecture. So we've made those observations, We've come up with a good solid statement, and we've written our own conjecture. Now, the other side of that is if we can find it false. So maybe they give us the conjecture and we need to find that counterexample that proves it false. You don't have to find every single case. Maybe you see more than one, but really we just need one that doesn't work. So the conjecture we're given is the sum of any two numbers is always greater than the larger number. So that what that says is A plus B is greater than A or B. So whichever one is greater, right, note there, whichever is greater, A or B, that A plus B is bigger than that. Now, a way to show that's true is if I said 3 plus 4 is greater than 4. That tells me 7 is greater than 4, and that's a true statement. That doesn't help us, though, because we want to show that it's false. So really, we could come up with a lot of options here that shows that it's true, but we still want that one that's false. Now, you're going to see, sometimes there's a pattern or a certain selection of numbers you can take to find counterexamples. One of them is 0. So if I do 0 plus 3 is greater than, well, the bigger number is 3, that is not a true statement. So this would be a counterexample. Another one that works is negative. So let's say I did negative 2 plus 1 is greater than 1. 1 being the bigger number. So I get negative 1 is greater than 1. That's false. This is another counterexample. We could go a step further and do two negative numbers. If we added two negative numbers together, those would not be greater. So right here we see anything with adding to 0, adding with negatives is going to be a counterexample. Either of those would work. In our second one, the value of x squared is always greater than the value of x. X squared is greater than x. Now, again, we can come up with a lot of ways that makes this true, but they're telling us to look for one way to make it false. Well, we tried 0 earlier. 0 squared is greater than 0. That's not true, so that would be a counterexample. Negative numbers, well, let's look. Negative 2 squared is greater than negative 2. Well, actually, that one is 4 is greater than negative 2. That one actually proves it true. You don't want that one. What if we tried 1? 1 squared is greater than 1. That's not true. There's another counterexample for us. And we could even go a step further and look at fractions. 1/2 squared is greater than 1/2. If I square 1/2, it's actually 1/4. I square the 1, I square the 2. And 1/4 is not greater than 1/2. So that is actually a counterexample. So any of those works. Any one does work. But what I would recommend as you go through problems like this, you just try certain numbers. 1, 0, negatives, and fractions will typically be the way to find a counterexample if one does exist, and it's these types of number problems. So look for, maybe we should say try. Try 0, 1, negatives, fractions. And with fractions, we could even say decimals. And typically, those would be the ones that give a counterexample, and that's in relation to them being identity properties and your rules with multiplication and adding with the negative numbers. So things to look for, kind of tools you have to go with. Now, the other thing we have in inductive reasoning is looking for a pattern. So we can describe the pattern and find the next one. If I look at 1, 5, 9, and 13, you can pretty quickly see that we're adding 4 each time. So we continue to add 4, and we get 17, 21, 25, on to there, and we add 4 to the previous term. We look at our next one, 3 to 12, 12 to 48, 48 to 192. Maybe you recognize that as multiplying by 4, which in fact it is. So we multiply 4 to the previous term. Probably multiply by 4 to the previous term. That would make our next one 768, and we can continue to multiply by 4 from there. Next one, -5, -2, 4, 13. What I like to do sometimes is just look at how it changes. We saw we added by 4, here we multiplied by 4. Here I'm adding 3, adding 6, adding 9. And we may notice there that 3, 6, and 9 are all multiples of 3. So with that thought, our next one would be 12, then 15, and continuing on with multiples of 3. We have 25 and 40 as our next two terms. So on this one, we'd want to say you add the next multiple of 3 to the previous term. Okay, so we looked for that pattern and we described it. Be careful in how you're describing things, as even with those counterexamples. Make sure you're describing your answer correctly. You want to be as specific as necessary when you do answer these. But again, inductive reasoning, you can be looking for those patterns, writing those conjectures, and if you choose to write that conjecture, you want to make sure it's as accurate as possible.